Thank you so much for joining. I'd like to start the online seminar today. Today's seminar is Exploratory Online Seminar number 93, Introduction to ANOVA Part 2. 2 weeks ago, we covered the Part 1, which was basically really the basic of how the ANOVA works, but using the very simple case, which is a one-way ANOVA. Today is basically on step up to from the one-way ANOVA. So today I like to introduce two-way ANOVA, which is one step above. But it's not that much of a complication. It's just bring in another level or another variable. So so let's get started. Before getting started, let me introduce myself. My name is Kan Nishida, CEO at Exploratory. We started Exploratory back in 2016 to democratize data science by providing a UI tool to do data science, and also having this type of seminar or training to share our knowledge and skills as well. So our vision is data-informed decision-making is the key, is critical to make the world better. Therefore, our mission is to democratize data science. When we say data science, we think is 5 pillars of the things you do, which is basically you want to access the data and then wrangling the data, meaning transform, clean up the data, prepare the data, and then visualize and analyze that data with various algorithms or various chart types and so on. And then last not least is the communication piece. Once you find the insights and you want to share with other folks on your team, in your organization and so on, so that you can make better decisions and also in a collaborative way. Okay. The Exploratory provides more than a simple UI to do these 5 things. So data access, data wrangling, visualization, analytics, and communication. Communication meaning you can create a report or a dashboard and monitor how your business is doing in an automatic way or interactive way. Okay, so enough about Exploratory and myself. Let's get started. So today, I'd like to do is Introduction to ANOVA Part 2, Two-Way ANOVA. Okay. So before getting started, I want to make sure you guys are familiar with the hypothesis test, because in this seminar, I'm not going to go into a thinking framework, what the null hypothesis, alternative hypothesis, p-value, and that type of the jargons in this seminar. I'm going to assume that you guys have, learned somewhere else or past seminars and so on. If you are not familiar with the hypothesis test in general, then I strongly recommend you go to our website, go to training and a seminar page under Learn. And then you can see the introduction to hypothesis testing. This particular seminar is really talking about how you want to approach and more by what type of how you want to think about when you approach the hypothesis testing, starting from the building the hypothesis, why the null hypothesis, and then going all the way down to what the p-value is. Okay, and then also we have done various other seminars as well about other hypothesis testing types or methods, such as t-test, Wilcoxon classical Wallis, and chi-square test, and so on. So today's topic, based on the last seminar, which is ANOVA. So another thing too, if you haven't, I strongly recommend you to watch the Introduction to ANOVA Part 1, One-Way ANOVA. So in this seminar, I really cover the kind of basic of the ANOVA. So without that, I'm basically this seminar, I'm gonna start off based on what we left off in Part 1. Okay. All right, so let's get started with Part 2. So ANOVA is a statistical test for comparing multiple means, so multiple groups. That's a big difference from a t-test. T-test can do only comparing the 2 means, 2 groups. This one, it can do the 2 groups as well, but also 3, 4, 5, 6, and so on. Okay. And then, so now I'm going to use the same example. So the question is, which school performed better on the math test? Okay, so we have a school A, school B, school C, and each row is a student in each school. And then we calculated the mean for each school. And then we visualize it. And obviously, like there's some difference between A, B, C, or among A, B, C. And that's a tricky part. Yeah, okay, there's a difference, but is that difference significant? Is that difference something that we need to care, or we should move on, right? So let's get this means. So we have like 3 means here. And our question is that this the difference between among these is significant. In order to answer that question, we want to find out the variance. And ANOVA is all about variance. So the total variance is something like this. So the center line is a mean of whole data, mean of all the data combined A, B, C schools. And then the total variance is the variance of all of these students, right? So the vertical dotted red line, that indicates the total variance of this data. And then the total variance can be decomposed into 2 variances. One is called variance between, and the other one is variance within. So these two things are the key components to do the test, ANOVA testing. So variance between, this is I cover in the part 1, but I'm just kind of try to refresh you guys so that you guys can kind of like start off or refresh your memories. Okay, so variance between is about the multiple means. So like we have 3 means, and what are the variance between these 3? To get that, like you want to get the overall mean, and then calculate the difference. So now we have 3 differences. And based on these differences, we can actually calculate the variance. So by squaring each differences, each of the differences, and then combine them together, and then divided by, in this case, 1, 2, 3. Okay, so that's a very kind of simplified way of saying calculating the variance. But pretty much that's it. I mean, like then you got to get into the degree of freedom kind of stuff, but I'm going to just consciously ignore it for now. To get the variance, basically, most important part is get the differences, square, and combine them together, and then get the average. But anyway, so I just kind of use this like a red dotted lines, the vertical red dotted lines that indicates the variance between these 3 means. Okay, so what is the variance within? Within is after you separate into 3 groups, and then like what are the variance in each group? So school A, the mean of school A is 77.4, and then all these students, 10 students, how are they varied? How they are separated, far from like their mean, which is like 77.4. Okay, so we calculate that like for each group. So like these are like basically the variance within. Okay, so this is variance within like the green, orange, and purple dotted line. And then the variance between, which is the red vertical line. Okay, and then basically like the question is this red or red variance line, is that big enough, right? So that's basically the question that we are trying to answer. So we basically like what we want to do is compare this red line against this dotted line, which are the variance within. And then basically they calculate the ratio. So that means variance between left-hand side, the red line, divided by variance within, so which is these dotted lines. And then what happens is if the variance between is relatively smaller than the variance within, okay, so like the left-hand side is smaller than the right-hand side, then the ratio will be less than 1. Okay, and then that means the difference among the groups are relatively small, meaning, this red line is relatively small, and which basically meaning that differences among these 3 means is not that big. That's kind of small. relative to the variance in the data, variance after you take the means out. Okay. So you can sort of consider the right-hand side, the variance within is basically the variance in the data that still sort of remain variance after you take account for the differences of those three means. So it's kind of like you can say like a variance that is not explained by the school differences. That's the variance within the right-hand side. Variance between, that's the differences that's explained by the school. A, B, C. Okay. So now like we are asking like, which school performed better on the math test, and then we can answer that question by calculating the ratio. If the ratio is to huge, bigger numbers, so that means probably is getting closer to the significant word. And if the ratio is small, then probably like we should just kind of like ignore like marginal difference and so on. Okay, so that was one-way ANOVA that we have covered last time. Okay, and then now here today, like I want to bring another question here. Which schools perform better on the math test if we look at the male and the female separately? Okay, so I just brought this like a sex variable, gender or sex, whatever you call it. Okay, so originally we had this data, right? So like we have the three schools and a green and orange and a purple. Now I brought another variable called sex, which has two values, male and female. Okay, and the female is pink and the male is blue. Okay, so what just happened here is these students were already separated by the school. But now by bringing in sex, and then we separated even farther. So what happened? So now like we get even more means. Okay, like now each group has two means, male and female. And that means we have 6 means. Those are like expressed as a dotted line, and as a pink or blue. Okay. And then now the question is, if I use a line, it can be visualized like this. And then now like the question is, does that make any difference? And also the school is still different. The school still makes a difference. And then the sex makes still the difference. And what is the relationship between? And those are the things that you can answer by using the two-way ANOVA. Okay, so like a one-way ANOVA, going back to the total variance, and except can be decomposed by one variable, so variable between and a variable within. In this two-way ANOVA, I'm going to just change the terminology a little bit. So left-hand side, I'm going to call it a variance between columns, or variance between, in this case, schools. Okay. But the right-hand side, I used to call it variance within, but let's call it the variance unexplained, meaning unexplained by the variable we have here, which is the school variable in this case. Okay. And then now we can bring another variable, which is in this case, sex, and which is a red square box here. And then what we are doing here is that like we separate the variance I explained, the upper part of the first above part of the variance I explained, separate into the variance that can be explained by the sex and the variance that cannot be explained, variance unexplained. So right-hand side bottom is really the sort of like error or residual or variance unexplained. Okay, so now we have basically 3 things: variance between schools, variance between sex, and variance unexplained. These 3 things came out from the total variance. And by using these things, then we can calculate the ratio, and then we can get to calculate the p-value, and then by using that, we can make decisions of like if that difference is significant or not. Okay, so this picture is the most very important. So now let's look at the original chart. So like these are, again, all the variance, and each circle represents each student. So originally, so this is the variance unexplained by the school. Okay, so those are the vertical dotted line. I want you to focus on the lengths of those dotted line. Okay. I mean, well, just, okay, the B is longer than C and A, that kind of stuff. But so I want you to remember how long are these dotted line. So now you remember, like, we brought another variable called sex and then make that, different color, meaning different groups. And then we can actually visualize the variance within each group. And remember, like, we have now like 6 groups, right? Like 3 schools multiply 2 sex. So like we have 6 groups. And then now look at that variance in each group. That's basically the variance within or variance unexplained, but in this case by school and sex. So compared to the original variance, that was unexplained variance by school, now these 6 variants, unexplained variance by schools and sex, become much smaller. I'm not sure like much smaller, but became smaller, right? And that is very important part of this Two-Way ANOVA. So because it became smaller in that picture is because I use the variable that actually can make it smaller. That means that variable, the sex, happen to have some relationship with the score, the test score. Okay. But what if that doesn't have any relationship? Okay, so maybe I brought something else, or maybe like I brought sex, and but female, male doesn't matter. So let's take a look at this case. Okay, so now like just by looking at this, looks like it's not like a female is better or male is better or anything like that. It's more almost like a kind of a mix in the middle, right? So that case, if we get the variable in each group, now like we have 6 groups, and then get the variable, sorry, not the variable, the variance in each group, meaning like a variance unexplained by school and sex. Okay. And it didn't really get much smaller, almost like, because, before or after you splitting into male and female, still the variance seems to be kind of same. Let's compare to the original one. Okay, original is like a green, orange, and purple. So the unexplained variance does not become smaller, did not get smaller. If the second variance, in this case sex, doesn't have a relationship with the target variable is a math test or test score. Okay, so it actually matters what variable you bring in as a second variable, but it's many cases like like, hey, you know what? There's another factor that will have impact or that will make difference in the target variable. Then in that case, obviously it's supposed to make the variance smaller after you bring in that variable. Okay, so then why this is important? Because ANOVA is all about the variance ratio, right? The ratio of 2 variances. One is variance between, and the other one is variance unexplained, or variance within, or error, residual, whatever you call it. Okay. And that ratio, we're going to use that ratio and then to make a decision if it's significant or not. So let's take a look. So if the variance between, let's say variance between schools or even sex or either way is smaller, relatively smaller than the variance unexplained, then the ratio becomes smaller, right? So that means that we can say the difference among the groups, in this case, let's say like schools, are relatively small and maybe like marginal difference. But on the other hand, if the variance between is compared and it's relatively larger than the variance unexplained, then the ratio will be less than 1. No, ratio will be, I'm going to just dynamically change this more than 1, right? Because the upper part is bigger. then that means the difference among the groups, in this case, let's say the schools, are relatively large. So let's take a look. So we have this like a variance between, okay, and then which is like a red line, and then compare against the dotted line, right? And then we are basically comparing like, which one is larger, which one is smaller. But when you look at here, now like we separated it by the female or male. So the variance unexplained became smaller. And then like when you want to compare against, then when you want to compare that variance between, which is the red line, against the variance unexplained or variance within, now it looks like the left-hand side, the variance between is larger or the bigger, right? So that means the ratio will become bigger, and therefore it getting closer, getting to the direction now being significant. Okay, so we've been talking about this like a particular one, like this like a left-hand side up, right? The variance between schools. But how about the second one? Like we brought that, second variable called sex, right? So that's the same thing. So we basically like want to know that if the difference between female and the male, that's significant or marginal. So then like what we can do is like, we can actually calculate the mean for each group. And then basically we can calculate the variance between these two, variance between. And then basically like we can actually get that variance within or variance unexplained. So now we have the 6 of those. And then basically compare these two things. Basically doing the same thing. But again, the important thing is the variance within right-hand side becomes much smaller because the school separated it, and then also the sex also separated it and make the variance smaller. Okay, and then so basically the same thing. We are comparing between the means among A, B, C, school A, school B, school C, or comparing between female and male in this case. Okay, so just kind of wrap up. So the two-way ANOVA is about minimizing the unexplained variance, right? So like we wanted to know if the school makes a difference, but also we need to account for variations between sex. In this case, particularly, obviously if you're interested in, and then obviously the sex makes a difference. And introducing another variance, in this case, the sex, another variable, sex, it can potentially reduce the unexplained variance even more by splitting the original unexplained variance into the second variance between and reduce the unexplained variance. So that's the two-way. And comparing variance between, against the reduced variance within or unexplained variance makes the test more powerful and more sensitive. So it may be that when you run that one-way ANOVA test, and then maybe the school didn't make it to be significant, but by bringing the sex variable, and if that makes a difference, then when you compare against the unexplained variable after school and after sex, then maybe that smaller variance might make the school significant. So that means that's the last part. So like this can make the test more powerful and more sensitive. Okay. So the idea behind ANOVA is to compare the variability that can be attributed to a particular factor with the variability that cannot be accounted for, which is that basically the unexplained variance. If you run the one-way ANOVA for school and therefore ignore the effect of sex, then the ANOVA will end up dumping all that sex-induced variability into the residual. And you're actually comparing against that residual. So therefore, the school might not make it. Okay, so that's the advantage of running the two-way ANOVA. Okay, so I want to actually kind of summarize like what are the cases that the result you might get when you run the two-way ANOVA, right? So this case, okay, so the blue is male, pink is female, and I'm just using two schools just to make it simple. Okay, school A, school B. So school A, school B seems like it doesn't make any difference. Y-axis is the score. Okay, and then even like you bring the sex and it doesn't make any difference. Like a blue and a pink is pretty much the same area. Okay, how about this one? So looks like school B performs way better than the school A. So we can say the school is significant. However, the sex doesn't really make much of a difference. Blue and the red, pink are pretty much at the same place. But how about this one? This case, the school doesn't really make much of the difference from A to B is basically flat. However, the sex makes a difference. It becomes score 70 to score 80, right? And then last one, how about this one? This one from A to B, the score becomes higher. So it looks like school makes a difference. And then the color from blue to pink is also significant. So the sex makes a difference in terms of school score. So in this case, we can say that both school and sex are significant. Okay. But how about something called interaction? So let's say like we bring A, B, C, and then in this case, from A to B seems like male and female, there's a difference. And the school difference, it looks like there's some kind of little bit difference there. However, when it comes to C, the male-female order flips. So now when the school C, the male is performing better than the female. So this is called interaction. And when you have this, then unfortunately, or fortunately, whatever, you can't really analyze the main effect, in this case, school or sex, because they're too intertwined. So we can't really see the effect of the school, or you can't really analyze the effect of sex because it depends the combination, it makes a difference. So they're kind of like very tightly kind of like connected between school variable and the sex variable. So basically, like when you run the two-way ANOVA test, like you want to find that if the interaction is significant or not. And if it is, then you basically want to stop there because you cannot really analyze the main effect of each variable. Okay, so you can expect this kind of result. Okay, so factor A, factor B, or variable A, variable B. In this case, like school and sex. Okay, so both of them are yes. That means both of them are significant. But then there's no interaction. And then like you can just analyze what how significant that is, what are the effect size, and also like maybe like you can even do the post-hoc analysis and so on, right? So now the second case, the school is significant but not sex, and there's no interaction. In that case, like you can just analyze that school A, right? And then the third one is only sex is significant but not school, but then there's no interaction. And then the fourth one is both of them are not significant, and interaction is also not significant. So that's, all of them are not significant. So that there's not much you can do about that there. And then the last one is that interaction is significant. And in that case, it says NA, which is basically missing value or whatever, because you don't even want to you don't care to find if this is significant or not for each variable, because there's an interaction is already indicating significant. Okay. So enough for the explanation. Let's get see like how this whole thing works by using exploratory. Okay. So I have this data. Okay, it's a very simple case, and we have like 18 rows. We have the drug variable, which has placebo, drug A, drug B. Okay, and each row is a patient. We are testing this drug, effect of the drug. On top of that, we also have something called therapy. So we are actually got these patients, and then half of the patients actually have been taking some of the therapy session. This is a kind of a psychological side of things. And then half of the patients are not taking any therapy in the past couple of weeks. Okay, so then we want to basically, in a one-way ANOVA, we did with this drug, and then we found that drug is significant. Okay, but also we realized that like actually like there's a difference between the patients in terms of like if they take the therapy or not. So we want to take that into our account. So we're going to bring that as a second variable. So we go to the analytics, and then what we want to do is like under the statistical test, instead of running the one way, we want to run the two-way ANOVA. Okay, and then target variable is a mood gain, which is like how much of the mood has gained after a couple of weeks after they take those drug. Okay. And then explanatory variable one, which is a drug. So this part is exact the same as the one-way test we did in the last session. So now here, we're going to bring in another variable called therapy. So now we have two variables, and then we run it. Okay, and here's the result. And it's very similar to one-way ANOVA, except obviously we have two variables. One is a drug and a therapy. And then the third, which is like a drug, this is like an asterisk, which is basically trying to say like X or multiply. Okay, so drug and therapy, these combinations or interaction. Okay, and then the residuals, basically this is the unexplained variance or error or variance within. And this total is a total variance. Okay. And then sum of square, which is basically the variance, except it's not divided by number of the patients, so like not like average. So it's just kind of just combined the square the differences. Okay, so that's sum of square, and then all of these combined together, and it becomes a total. And this sum of square SS ratio, which is basically total is 1, and what's the percentage of that variance? Okay, for each. And then there's a degree of freedom. And the degree of freedom is basically the divider for the sum of squares to calculate the mean sum of square. And once you get the mean sum of square, basically this is really the variance. So then we get this variance, then you want to do the calculation of ratio. So for example, this drug, and then if you want to calculate that by, you remember this one, residual, instead of, no, there's no instead, there's residual. So like this is like unexplained variance, and then you want to use that to divide this drug variable. And this one, I actually keep the one-way ANOVA here. There you go. So this sum of squares 3.45, and then the mean square 1.72. This should be the same, but residual is a 0.09. And this one, doesn't have the therapy. So the residual is still relatively larger because that probably has some like a variance of the therapy. Okay, so now look here, when you go back to two-way ANOVA, so now this mean square, here, 0.05 instead of 0.09. So it's got reduced. And then use that to divide this 1.72. So like the F value tend to become bigger. Okay. And the same thing for the therapy. And the therapy is a mean square, the mean sum of square, or the variance is 0.46 and divided by this residual 0.054. So then it becomes 8.58. Okay. And then the drug and therapy is the same. And then like we can calculate the p-value. And then the p-value is, in this case, the drug is this chance or the probability of getting this F value if we are based on the assumption of null hypothesis. In this case, drug and mood gain doesn't have any relationship, or there is no difference among all those drugs. That's a null hypothesis. And then based on that, what is the chance of getting this F value 31, which is pretty high, which is 0.000016. So basically 0.01%, 0.016% of the chance that you get this value or more extreme or larger numbers. Okay. So anyway, so this is a significant, if we use that like 5% or 0.05 as a threshold, then we can conclude the drug is significant. Next one, the therapy, 0.01 is the p-value. And again, if we use 0.05 or 5% as the threshold values, and then we can conclude the therapy is also significant. Okay. And then the next one is drug and therapy, this interaction. In the slide, I said, you gotta look for significance of interaction first. And yes, I actually did the opposite, but I was supposed to check this one first, and the interaction is 0.12. And if we go with the 0.05 significance threshold, then this is larger. Therefore, this is not significant. So that means we can carry on the analysis on the main effect, which is a drug and therapies, therapy. Okay. But if this value is 0.001 or something like that, the smaller than the 5%, if we go with the 5% threshold, then this is significant. That means we're going to stop right there. And we can say, hey, it's too intertwined between drug and therapy, so we can't really continue on that analysis. Okay. So that's the analysis here based on, the question of to answer the question of significant or not. Okay. So now next one is, now that we know that drug and therapy, both of them are significant. And, oh, by the way, this one, drug and therapy, we actually use this p-value to conclude this is not significant. But also when you go to the means line, this tab, and this is where you can see, I'm gonna just hide the confidence interval to make it simpler. So this one, the orange color is a no therapy group patients, and the CBT is whatever the therapy these patients are taking. And then there's a drug A, drug B, and a placebo. And then the key thing is these two lines shouldn't cross. If we cross, then there is a significant interactions going on. So we can't really analyze by using ANOVA. Okay, so this chart also shows us those they're not intertwined or we don't have interaction, but also we can come back here to see this interaction row that's not significant. So it should come as conclude the same result. Okay, but anyway, there's that. And then next thing I want to see is like, so what is the effect? What's the effect size for each? So drug and therapy. So there are a couple of effect metrics for effect size. And then you can actually click on this icon to see the explanation and also the guidance. In the one-way ANOVA, we cover this ETA squared. But for two-way ANOVA, which want to actually check partial ETA squared as well. So like I'm going to just quickly explain what the difference between those two. Wait a second here. Okay. So ETA square is basically the sum of squares for the between divided by sum of squares of total. So basically the ratio of the sum of the squares of a given variable, which means that when you look at the second column, SS ratio column, that value is exact the same as the ETA square. And then when you were doing a one-way ANOVA, this is the partial ETA square. The ETA square is basically the same, and then that's okay. Doesn't have any problem. But when you want to do the two-way ANOVA, some people recommend partial ETA square better because based on this calculation. So partial ETA square, instead of dividing the sum of the square of the variable, in this case the drag, by the total variable, instead you want to take the variance of another variable, in this case the therapy, and also interaction out. And then you want to use only the residual and the variance of the drug, and then make that as a total. Okay, so basically total minus variance, sum of squares of another second variable or interaction. Okay, so that is the divider. Okay, so therefore this partial ETA square tend to become the larger than the ETA square. Okay, and then like you can see like what's the effect size, because the way to think about it is how big of this difference against the unexplained variance, right? So that's sort of basically kind of thinking behind. So when I calculate here is basically 3.45 divided by 3.45 plus 0.65, and it ended up becoming 0.84. I mean, in the real calculation, you need to add more like digits there, but I just made it simplify. But still, nonetheless, it's pretty much the same number. Okay. And that's the partial ETA squared. The one key thing, something to think about here is that ETA squared is a ratio, and then you can actually compare among variables. So what is the ETA squared? Sorry, not ETA, eta. That's I think the Greek word. But either way, yes, I can't call it ETA. But eta squared is like a drag. For drag is a 0.71, which is a lot bigger than the eta square for the therapy, which is 0.09, right? So by looking at eta square, we can say like which effect is bigger, right? But now the partial eta square, which is like the therapies is 0.41, right? So that's actually kind of confusing because I'm talking about here 0.41, and then because the drug is 0.84 and the therapy is 0.41. If you were just paying attention to only these numbers, and you can't stop comparing these two, and it's almost like, oh, okay, the drug's effect is the double of the therapy. But then when you look at the eta square, it's not just double; it's almost like 7 times. The drug is bigger. So that's the trick part, because in order to calculate that partial eta square, what this is doing is that like you want to get 0.46 and then divide by 0.46 plus this residual variance. Okay. So therefore, this tend to become bigger because you're not caring about, it's almost like your starting point is there's no any variance, reduced by the drug, right? So that's, you don't care about that at all. And then you're just comparing 0.65, but that 0.65, the reason we have the much smaller variance here is because the drug actually reduced the variance in the first place. But that partial eta square doesn't account for that. So therefore, the partial eta square is to really focus on the effect of the particular variance, but how a variable. However, you don't want to compare among these numbers. You don't want to compare 0.84, 0.41, such things. If you want to compare, then you want to go back to eta squared. Okay. So, and then last not least, which is a post-hoc analysis. I covered that in a kind of detail, like why the post-hoc analysis is slightly different from the other way of like comparing things, because we have to run multiple tests in a part 1 seminar. So if you want to know more about detail or basics of a post-hoc analysis, please take a look at part 1 video. But I'm going to just cover a little quickly here, which is basically now that we know, let's say the school is different and also the sex is different. Our use case in what we saw in the exploratory, now we know the therapy, the drug is significant, and then therapy is significant too. But we still don't know like where is that difference, where that difference is coming from. So for example, going back to the slide, school ABC, are we talking about the big difference between AB or difference between AC or difference between A and C? But also we brought another variable, which is in this case, the male and the female. So are we talking about this difference? So there are 4 combinations and 4 patterns, right? So in this case, let's go back here. So we're talking about drug, and drug has 3 groups. So what's, where the difference? And the therapy is like there's 2 groups, so there's only 1. But it's that difference. So we want to know about that. So you can go to the comparison bracket variable, and this is where you see, okay, so drug A and drug B, drug A placebo, drug B and placebo. There's 3 tests, right? And also another thing is therapy. This one has only 2, so we don't have to worry about different combinations. There's only 1, but still, so we want to run 4 tests here. Okay, and then we are running the t-test for each combination. But the default, we are actually running a 2 keys HSD test, honestly significant difference test, which is basically like taking into account that we are running this like a hypothesis test multiple times. So we still want to control the type 1 error, and then while keeping type 1 error under the control, and then we can still make a decision based on this p-value. Okay, so that's the attack is HSD test is default. If you prefer, there's other type of the test as adjustments as well for the p-value. So but we can go with the default. And then here, like we can see, except the drug A and the placebo, all of them are significant. Okay, so this time there is no interactions, but also we want to know, we might want to know the interactions for this post-hoc analysis as well. So what that means? Well, you remember like we have in this case 6 groups, right? So the school case, the schools, 3 schools, and then the male and the female. Our case in exploratory is like 3 drugs types. I mean, 1 is a placebo, but 3 types, and then the therapy or not, right? So basically we have 6 groups. So that means where's the difference? Like we can actually just go into more detail of, in this particular case, school A, and then the gender is female. And that means that can be compared against 5 other groups, right? So how about like the difference between of each combination? And then like we can actually do that for like each group. Then we're gonna have like a lot of groups. And that you can actually go to comparison and interaction. So this is where you can see like drug A, and then even the drug A, and then the patient that taking drug A, and then is taking a therapy or not taking a therapy. Okay, and then here in the second one, the patient taking the drug A and taking the therapy, and then the patient who's taking drug B and taking the therapy. So like all sorts of different combinations. And then like you can see that significance here as well. Okay. Okay, so that's basically the post-hoc analysis. And so just to wrap up, I think two things I just wanted to touch base at to wrap up. So one is this thing, right? So basically total variance, and the ANOVA is all about variance. I mean, comparison of the variance, the ratio of the variance. So to get the variance, you start with the total variance, and then one-way ANOVA is to bring the one variable and then calculate the variance between the variable and then the variance within or variance unexplained. Two-way ANOVA is to bring another variable to reduce the unexplained variable by bringing another variable. Okay, so and then once we get this, then we want to calculate the ratio by using this unexplained variance. Okay, so that's really the ANOVA. And then once you get that, then the rest is basically the same as one-way ANOVA, except there's an interaction. And then once you have the interactions, so you want to, because you have two variables, you want to look for the interaction first. When you have the interaction like that, then your analysis stops there because those two variables are too intertwined. If it's not, then you can continue on the analysis and see each main effect or each variable is significant or not. And also, like you want to go carrying on the post-hoc analysis and see where is that difference. Okay. All right. So that's it for today. Please make sure like we go to our website, and then there's a menu under the Learn. There's a training and seminar, and after on that page we show like a future seminars or upcoming seminars, and also the past seminar recording. Past seminar recording, you got to go scroll down to the bottom, and there's a link, and then like you can check up that whatever the past seminars. And then if you click one of them, each of them, and then it will open the page with the YouTube video embedded in. And also, if you're an exploratory user, please make sure go to our website under the Learn. You can find a lot of tutorials and also video. And also like a chart gallery is if you're using chart, definitely I recommend not just like how to use various different chart types, but also a lot of like a chart features that I can explain there as well. Okay, other than that, if you have any question or any feedback, please reach out to me at kan@exploratory.io. And also we have the Twitter account at Exploratory Data. So please follow us. And I think with that, I think that's pretty much it. If you have any question, please let me know. Otherwise, that's it for today. And thank you so much for joining, and hope to see you next week. Bye.